Hey everyone, my name's Clancy. I'm an assistant professor in the Department of Geography and the Berkeley Center for New Media at UC Berkeley. I'm presenting, thank you for coming to the talk. First of all, I know it's sort of this new hybrid era we've entered, and so, sorry, I'm just timing myself so that I know that I'm going to not talk over. So thank you for coming. This is I'm going to say work in progress. So it's fairly experimental still. I'm keen to hear what you have to say about it and what you think. I think without much further ado then, I might just start going and we'll see how we go. Okay, I'm just going to share my screen. Okay. Awesome. So Cartopia presents an atlas of maps created by artificial intelligence. A reckoning between carto and topos, cartography and place, this atlas is an exploration of how landscapes are mapped, how maps are read, and how computers might do both. Where some maps reflect utopias, dystopias, heterotopias, places good, bad, or diverse, these maps simply reflect maps, cartopias, places that only exist in cartography. Generated from a cooperation of millions of pixels and probabilities, Cartopia holds evidence of both cartographic and computational processes, in post-human contradiction and collaboration between people and machines, between human meaning-making and computational reasoning. And they were produced using a suite of generative adversarial networks, which learn, generate, style, and upsample, producing what are better described as collective experiments in probability with the result of a deep understanding of cartographic practice. From a series of 10, it will be 10, this is 3, different cartographic styles, this atlas presents places and landscapes that have never existed, a figment of the conversations hosted by an artificial intelligence, a product of its gradual learning and agreements about the history of cartography, and whose likeness is a mimicry of a creative process that used to be undertaken by people. Thus, Cartopia is both map and territory, image and landscape, real and fake, singular and plural. Each map in this atlas skates across the uncanny. Strange familiarity haunts this cartography that cannot be read, that becomes less comprehensible the closer the eye gets. Like a blur in the eye, a word on the tip of the tongue, an image that slips from grasp, a touch that is not quite made, a smell that lingers, it leaves an unfulfilled promise, a question never answered. The landscapes depicted are illegible, yet eerily familiar, reaching into the uncanny tensions of our familiarity with maps, leveraging our ability to translate across the distance between the tools a cartographer uses to communicate and the heterogeneity of the places and spaces they purport to represent. From classification to representation, cartography has always been partial. An artificial intelligence, like a map, embeds the world in incomplete logics, the necessity of abstraction and generalization, the optimism of the coder or cartographer, and the limitations of technology. That we consider that these tools ought to reclassify, remeasure, and redraw the world is perhaps more of a post-human era than a computational one. Like most artificial intelligence, Cartopia too is partial. Its generative adversarial networks depend, infant-like, on the collection of images given to them that each network shapes and reshapes and remakes. While Cartopia builds on the disciplines of cartography, its traditions and its standards, the maps inside are different kinds of maps. Each map is a map of maps, as the generative adversarial network takes the image of the cartographic coordinate grid and transforms it into the computational coordinate grid. Each line becomes a disjointed series of pixels, each color a set of numbers, each image a series of layers, transposed down and down again, shaped and reshaped. The result? A series of trickster objects that trade on our training and desire to read a map, but disentangle and confound our smooth cognition between symbols and landscapes. The labels are unreadable, the colors are meaningless. Geographer Emanuela Casti argues that maps are not simple objects that reflect external realities. Instead, she posits that they are representational agents that produce and shape our realities. Maps provide the language and tools for meaning-making, which we use to understand the world. Cartography has become so embedded in geographical modes of thinking about space, what Said has called the cartographic imagination, that we begin to see the world through the map and as the map. The cartographic imagination can be found across spaces and times. The maps in Cartopia are exemplary of, to quote Jean Baudrillard, an endless procession of simulacra, representing landscapes that only came into existence through the process of mapping, but do not exist anywhere else. The hundreds of maps produced and the dozens curated in this atlas are the result of tens of thousands of maps gifted to generative adversarial networks to learn from and to build. Generative adversarial networks, or GANs, are a specific class of deep learning systems or frameworks that generally use a combination of convolutional and deconvolutional neural networks. Importantly, GANs, generative adversarial networks, are dialogic. They are composed of one section, which generates images, and another which discriminates, or decides how close the generated images are getting to be a verifiable mimicry or simulacra. The GAN is given upwards of thousands of digital images, where it reads each of the millions of pixels in each image, taking into account where the pixels are, what color they are, and then on a balance of probability learned from these images, the generator makes a new image. Pixel A is in probability black, pixel B, white, pixel C, blue. Then, the discriminator tests how close the generator has come to the original database. Does its choices fall within a ratio of probable original, or is it more obviously a fake? This process repeats for a number of cycles or epochs as it gets closer and closer each time. The GAN then is a parasitic forger, leeching and converting data from a host, whether server or data, producing new fabulations in a fabulous mimicry. GANs understand patterns deeply and follow them. Flesh-colored tones are more likely to be grouped together. The border of a map is usually blank. Computation is not so different from cartography. Wendy Hui-Kon-Chung writes, the logic of programming reduces the living world to dead writing. Programs condense everything to source code, written in advance, hence the adjective source, end quote. The structures that underpin modern computer programming are codes, representational structures that abstract and generalize the world into sets of symbols and actions. There are hundreds of different coding languages, which translate into slightly different logics, some with better focus on calculation, some with better focus on interactive activity, appearance, or filing. Yet, unlike other representational systems, the act of writing code or representing objects through a series of commands collapses the distance between representation and action. Returning to Casti, maps construct realities as active agents, but still require something else to build those realities with cement and steel. Code, however, does not simply represent, but realizes. This distinction is the difference between data and algorithms, between information and action. Computation instills in code executive actions. A programmer writes code and in doing so tells it what to do. This might be as simple a command as showing the RGB values of a certain pixel, or as complicated as reading thousands of maps and in conversation with other networks of code, making new ones. This means there is also a difference between maps made using computational tools and maps which compute. The political consequences of maps which compute can be found in the story of how computation and cartography came to intertwine through geographic information science, radiotelegraphy, and global positioning systems, and how it transformed territory into a globally connected network of points on a world grid in the latter half of the 20th century, to cite William Rankin's After the Map. Yet, in terms of maps made using computational tools, we've also seen the vast digitization of millions of maps around the world, paper or canvas or vellum objects photographed, rendered into colored pixels at a high resolution. This is a secondary abstraction and generalization of the map. The paper map, at a scale of 1 to 50,000, is transformed into an image with a resolution of 300 pixels per inch, or a total of just under 97 million pixels for an image 9,000 by 11,000, which is usually the size of archival images. The loss of information in the translation from paper map to digitized map, or pigment to pixel, is impressively minimal compared to the loss of information in the abstraction from landscape or original to map or referent. And so the endless procession of simulacra begins. The map becomes a territory better mapped by a computer than the territory was mapped by the map itself. It is these digitized maps with which the generative adversarial network, in this atlas at least, works. The GAN makes maps from maps of maps, not maps of territories. Indeed, the map has truly become the territory. However, to return to the endless procession of simulacra, cartographers also lean heavily on the past. Mapmakers have a long history of copying other maps to the point where cartographers would create fake streets or places to assure the copyright of their work. This calls into what Simon Ryan has called the cartographic eye, or what I might call here, as a sort of advance of this idea, the computational eye. Ryan's study into Australian art and cartography during the early colonial period reveals a distinctly cartographic vision dominated by geometric perspective, enacted as a territorialization of the landscape through order, metrics, and lines. Unlike the cartographic eye, though, the computational eye is focused on the microgeography of the pixel rather than the macrogeography of the image. It does not see points or lines or polygons, nor does it see the coordinate grid which underlies the production of contemporary digital cartography. Instead, the image is a network of pixels, and the pixels give the two-dimensional image its depth and dimensionality, 2, 3, or 4 channels in their own numerical way. Thus, the shape of the digital image does not refer to the Euclidean geometry of the cartographic eye, but rather the multi-scale and network numeric data of the computational eye. Like a cartographer, the computational eye can stretch and reshape a digital image according to different strata of data. Never said that out loud. While the image has a geometric shape defined by the number and kinds of pixels it contains, each pixel also has several geometric parameters defined by position and hue. Just as a cartographer may look at a landscape or a database and see environmental data or social data, the computational eye can build and rebuild the cartographic image from multiple perspectives across scale and gaze, so much so that it is possible to separate it out and look at its parts and then put it back together again, to see it as a collection of individual pixels each with 3 channels, or as 3 different channels or 4, each with numerous pixels. But it does not necessarily comprehend the meaning of the image it restructures. It does not learn about geological formations, nor does it learn about fire risks. Instead, it imposes its own computational logics on this territory and rewrites it accordingly. In this reading, the territorialization of these digital cartographic images through visual computing is so deeply reminiscent of the process of cartography that where cartography colonizes landscapes, arguably, computational colonizes cartography. It reaches the cartographic image from another, also partial perspective, and drawing from its learnings makes new maps. Thus, where Turnbull argues that maps are territories, in this case, the thousands of maps which make up the image databases from which the GANs learn are indeed territories over which the computational eye casts its gaze. Fundamentally, the grid, though, of visual computing is different to the coordinate systems we have come to understand as underpinning the principles of geographic information systems and digital cartographic visualization. This grid composes the image itself, not a database of information pinpointed in the world. When Gunnar Olsen writes of Marduk casting a net over land to establish the first grids, it is also possible to imagine the same kind of grid being cast of the cartographic image in the process of digitization into bitmap, a neocolonialism of the cartographic image itself. But in doing so, the GAN picks up on other elements we might ignore in maps and asks us to reckon with both our present cartographies and computations. At least part of the premise for this atlas came from the questions arising out of Edward de Bellamy, the artwork, the AI artwork that was sold recently for a lot of money, and the wave of artificial intelligence art that has followed. Artworks like these might tell us something about the depiction of landscapes and people, artistic styles, and the way in which we read and view art. But often, like these cartographic images, they will have generated imperfections, marks or gaps in the map, artificial agency, aging as the image color has faded. And so there are accidental investigation into the relationship between material and digital archives, how we read visual objects and make sense of them, computational rereading of the repetition and rupture in our visual styles. So the maps presented in this atlas, made by a computational cartographer, are more persuaded by pixels and projections, are more inquiries than they are statements. And so the key question in asking a generative adversarial network to make a map was simple. What happens when a computer colonizes the cartographic image in the same way that the cartographic image has historically colonized the landscape? What can a neural network learn from a map, and what can we learn from the maps it makes? So this is a purely relational map, which refers into itself using color, line, and text to demarcate different, but leaves a crucial answer or question hanging. Difference of what? In this way, cartopias offer a stability of cartographic objects. Here is a heading, here is a border, here is a legend, here is a scale, here is a label. But without cartographic meaning. What name is this place? What extent do we see? What objects are being mapped? Ontological stability, without epistemological meaning, is very much the realm of the neural network, a false security into which, as McKittrick argues, we place too much power, a network that sees relations without meaning. Through these strange methods, strange maps are formed. Nana Verhoef argues that indexicality, or deixis, is central to the way in which we read and navigate using maps and cartography. Gunnar Olsen, on the topic of spatiality of self and other, has argued similarly. The indexical distance between a thing and its representation is fundamental to geographical inquiry. And so when we see such strange depictions of landscapes that no person has ever visited, no scientist has ever surveyed, and the legacy of cartographic traditions deformed and reformed to make the maps that have produced Cartopia, we can see the workings of both cartographer and computer in a different way. Thank you.